Okay, hello everybody. Welcome to the NCL Land-Based Railway Cyber Twin training video. Here is a quick overview of what we will be covering in this video. Today, we'll be exploring an overview of how the railway system works, what human-machine interfaces are available, and how the network has been set up. We will assume that you have a basic understanding of computer networking and virtual machines. We will also assume that you understand how programmable logic controllers, PLCs, and remote terminal units, RTUs, work. If you do not know these, please watch the previous training video so that you can follow along with this video. By the end of this video, you will be able to identify and explain how the railway system functions on a high level and be able to comfortably navigate the NCL railway system interfaces. Now, let's look at what we'll be covering in this video. Firstly, we'll be looking at a top-down view of how the railway system works and how it is constructed. Next, we'll be looking at the network diagram to see who are the users of the system and what VMs exist in the system. We will then go through the different interfaces, or rather human-machine interfaces, that are being used by the system users. Lastly, we'll be going through the points of access that are available to you and how you can start interacting with the system. As a cyber twin, the railway distills a normal railway down to the bare-bone essentials. The railway consists of 3 train tracks filled with signals, sensors, stations, and junctions, and there are 10 trains that move along these tracks. A track block refers to a part of the tracks. We will explore why track blocks are useful in the next training video. The train's power and speed are controlled by a virtual machine that handles train controls. As the trains move along the track position sensors detect these movements. They send the train position data to the track signaling system, which we will go into further detail later on. The track signaling system sends its output to the signals, which the trains will read and act to accordingly. This controls when and where these trains can move. This includes moving across junctions, stations, and track blocks, which are controlled by one virtual machine each. Let's now take a look at the network diagram. To replicate real life, or rather simulate real life, there are system users and departments that have their own subnet in the network. There are clearly 3 distinct subnets identified here: the operational room, the maintenance department, and the engineer department. These 3 subnets are separated with a firewall, so any unauthorized packets cannot be passed from one subnet to another. Let's go into more detail of what each of these departments are. Firstly, let's talk about the maintenance department. The maintenance department is meant to simulate the maintenance engineers in real life, people that access and check up on the machines such as the PLCs. Maintenance department VMs will have a prefix of rail-md in their VM ID. Currently, there are no user VMs in the maintenance department. The physical real-world simulator, whose VM ID is PW, is actually the level 0 part of the system. This is a digitized version of the real world, which serves to replicate the actual physical wiring and components. It is meant to help you visualize what a railway system looks like and how OT attacks would affect each railway component. As a result, although it sits in the maintenance department, please do not directly attack this VM. The subnet mask is as follows, to help you find out which VMs are part of the maintenance department subnet from their IP address. Next, we have the engineer department. The engineer department subnet is meant to simulate the railway system's logical components that the railway components communicate with. Currently, there are no user VMs in the engineer department. There are 5 machine VMs in this subnet. Each VM simulates a different part of the railway system. The first VM is a track junction VM, which handles the logics for PLCs 0 to 2. The second VM is a track station VM, which handles the logics for PLCs 3 to 5. The third VM is a train control VM, which handles the logics for PLCs 6 and 7. The fourth VM is the track block VM, which handles the logics for PLCs 8 and 9. These four VMs control the entire back-end logic of the railway system. Lastly, the fifth VM is the Remote Terminal Units VM, the RTU VM. It manages and runs the program for 10 RTUs, where there is one RTU for each train. We will go into detail on what the RTUs do later on. And finally, we have the operational room. The operational room subnet is meant to simulate the railway control center in real life, where users can view and manage the whole railway system from. Operational room VMs will have a prefix of railway-op in their VM ID. Currently, there are no user VMs in the operational room. There are 3 human-machine interfaces that are accessible in the operational room, each providing a different visualization of a part of the railway system and different ways that they can interact with the railway. We have the Railway Signaling Monitor SCADA HMI, the Railway Track Block HMI, and the Railway Trains Controller HMI. We'll go into more detail of what each of these HMIs do later. Let's first talk about how to interpret the physical real-world simulator. Do remember that this VM is not to be attacked, as it is implemented for visual purposes. On the left side of the physical real-world simulator, we have a trains control section. Let's start from the top. Firstly, we have the power on train button, the emergency stop train button, and the reset train to default position button. These 3 buttons directly interact with the system and do not actually communicate with the train control or track signaling part of the railway system. The railway system consists of 3 railway lines. Firstly, we have in green with 4 trains. Secondly, in yellow with 3 trains. And lastly, we have red with 3 trains. Lastly, we have the checkbox for the auto collision avoidance system on all the trains. This checkbox is a getter and setter for the actual avoidance system on the trains, which lets the trains detect if there are any trains ahead to prevent collisions. We also have the 4 PLCs VM's connection states, which tell us whether the PLCs are connected to the physical real-world simulator. An offline connection can either mean that the PLC is offline or it is unable to communicate with the real-world simulator. As mentioned previously, the 4 VMs are divided into 2 parts, the track signaling and the train control. Each of these VMs controls several PLCs. The track junction VM controls PLCs 0 to 2 and so on. On the right side of the interface, we have the RTU connection state as well as the legend. Let's move on to the center of the interface. There are 5 railway components to take note of here. These are the same as before. The train station is indicated by a large rectangular box with a circle inside. The train is indicated by consecutive boxes, which may be green, yellow-orange, or red depending on the speed of the train. The railway track signals are indicated by the popped-out boxes, which may be green or red depending on whether they are open or closed. For the last two components, we have firstly the junctions, which are indicated by the green boxes where one train line intersects with another line. And next, we have the train position sensors, which are indicated by the small grey boxes that are at fixed intervals along each of the train lines. These are the three human-machine interfaces that you'll be able to interact with. The Railway Signalling Monitor SCADA, the Railway Trains Controller, and the Railway Track Block. These three HMIs can be attacked for your OT attacks, as opposed to the physical real-world simulator. Let's move on to the Railway Signalling Monitor SCADA HMI. Looking at the interface, we have firstly the train station docking sensor, which flashes yellow and blue when triggered, and grey when not triggered. Currently, the arrow is pointing to one that is not triggered, meaning there is no train currently at the train station. Next, we have the junction block sensor, which is red when it is on and green when it is off. When it is red or on, it prevents any train from moving forward into the next track block. Moving downwards, we have the PLC connection statuses for the junction and station PLCs. Firstly, we have the PLC digital input, which is indicated by the green, red, or orange boxes. Then, we have the corresponding PLC register state voltage, which is green when it is high and grey when it is low. Looking at the right of the interface, we have the track position sensors. These flash yellow and blue if a train is currently on the sensor, and grey if there is no train currently on the sensor. We can see that there are many of these thin lines that connect two different train lines together. These are the connections from the sensor to the signal for junctions. When a train passes by a sensor, the red lines from the sensor will block the corresponding signals, turning the signal red. The green lines from the sensors will unblock the corresponding signals, turning the signal green. Moving downwards, we have the PLC digital output and the corresponding PLC coil voltage. The PLC coil voltage will be green if it is on and white if it is off. Let's now move on to the Railway Trains Controller HMI, which summarizes all of the train's information into one HMI. Moving on to the left of the interface, we firstly have the current speed indicator, which is presented in a visual form. This differs from the average speed indicator, which is presented in the textual form. The average speed is calculated over the past 10 seconds. We also have the power on train button and the emergency stop train button. This sends a signal to the train control PLC, so this can be attacked as opposed to the physical real-world simulator buttons. We also have the current and voltage indicator on the right side of each train card. Note that each train has its own control card and are controlled independently of each other. On the right side of the interface, we can see the connection status of train control PLCs, with the PLC register state and PLC coil voltage displayed the same as before. The coil voltage is on for high and the register state is green for high. There is one input register and one coil for each train, and they follow the same numbering as the train cards. There is also a PLC coil that does not correspond to any specific train. This is the collision avoidance coil 10, which ensures all trains do not crash into each other in the event that they are in the same track block. The button for setting the call set request for the collision avoidance call 10 can be found at the bottom right of the interface, but please do not toggle this. Let's move on to the next HMI, the track block HMI. In this HMI, we have the track block signal override control, which is ticked for default and unchecked to stop any signal changes. This means if the signal is green, the signal will remain green, and if the signal is red, the signal will remain red. The block controller override has been disabled for the station and junctions for now. And on the right side, we have the connection status of the track block PLCs. With that, you should be able to connect to the VMs and explore what each of the VMs and HMIs are capable of. The instruction manual of how to connect to these VMs should have been sent to you separately. Do refer to that to connect to the servers. Now, that's the end of this training video. I hope you now understand and can explain how the railway system functions on a high level. In addition, I hope you are able to comfortably navigate the railway system interfaces like the HMIs and the physical real-world simulator. Thank you.